I will show how artificial intelligence can be applied in the semantic web. Initially, they were like the research result of artificial intelligence can be used for the semantic web research community. So I will demonstrate that one. So first, I will present some overview about the paradigm shift in the web. There is a paradigm shift in knowledge exchange or data publishing in the web. Usually, the web is owned by what we call the W3C, and W3C sets standards about the web, how to publish data, how to publish document. So there is a paradigm shift. I will show that one, and I will also show how that paradigm shift goes to graph data, because I will be discussing on that. Then application of machine learning on graph data. Then we propose this graph data. You need some deep learning technique, and we come up with a deep learning technique which we call it as tensor calculus. Okay, so the paradigm shift was made in knowledge exchange by W3C. I can say that the major source of data for any kind of analytics is the web. So we cannot deny the contribution of the web for data analytics or for data science. Even one subdiscipline of data science is data creation. So the data creation part of data science is done by the web. So the issue was, it is like in 2001 when the semantic web was introduced, the W3C made some standard shift. That shift was, it encouraged people to publish data than document. So after 2001, data became citizen of the web. But after that, like in 2006, data is not becoming the citizen of the web, but it becomes the first class citizen of the web, because W3C encourage people to publish data than structured documents. So that the shift was, there is change from publishing document to data. Then later on, there was a shift of publishing what you call data only. So data become first class citizen of the web. So for data publishing, W3C once again established a standard data publishing model. That standard data publishing model is RDF, or Resource Description Framework. If you can see RDF, it is a graphical data model. Maybe if you need some introduction about how this RDF representing is, it represents information in the form of subject, predicate, object triple, and a subject can be a node, and the object can be a node. So the two can be related by the property or the, so this forms a graph. This forms a graph. Based on this data model, currently huge knowledge bases, sometimes we call it knowledge graphs, are published. A typical example is, for example, Wikipedia. Can you see this? This is a data published in the web in Yago knowledge base. So you can see this is a graph. This is a graph. There is one node in the middle, and there are some other nodes, and these nodes are connected by what we call some relation. We can represent this into a graph model, which that is why I said RDF is a graphical data model. So the effort is not only publishing one database or knowledge graph in the web. There were efforts to publish many knowledge graphs. So currently, maybe these days, in the web, we have this much knowledge bases. Right? So the web is now becoming a single global graph. So one data source is connected with the other. One data source has a set of RDF triples. If I consider, for example, the central data source, which we call it DBpedia, it talks about like 5 million instances. So in general, in the web, we have around 100 billion factors. 100 billion factors. So the issue is the initial motivation to publish factors or using RDF data was it was to achieve next generation information retrieval goals. The next generation information retrieval goal is giving fact, giving answer for our queries, not a list of documents that talks about our query. So that initially, when the semantic web was initially what we call conceived, it was to give answer for queries. So how much was that successful? You can see some examples. For example, in Google, there is Google Knowledge Graph, if you know, if you are aware of it. In Microsoft, there is what we call Satori. In IBM, we have the Watson. They are based on knowledge graphs. For example, if I write a query, what is the capital city of Ethiopia in Google? Usually the answer for this query is extracted from a knowledge graph. The knowledge graph is not the only source. It can also be extracted from unstructured text using some learning approach, but the primary source is DBpedia or some other sources. So, for example, the Watson Jeopardy search engine, which wins what we call human expertise, was based on the 3 knowledge bases. One was DBpedia, and there was 3 knowledge bases. So, you know, the purpose of this knowledge graphs or publishing graph data on the web is to achieve query answering or question answering, which is the goal of information retrieval for the next, which is a research agenda of information retrieval. It can also be, there is too much progress in knowledge management because of this knowledge graphs. If I write a query about Champions League, I can extract answer from what we call from the source because it is extracted from the knowledge graph. I can also get summaries, facts about some entity because of knowledge graph. I can even use endpoints. For example, there is a DBpedia endpoint. So I can write a query by saying, for example, this query is saying DBR Ethiopia, DBO capital, then the last one was a question. So I'm saying like, what is the capital city of Ethiopia? So you know, the natural language query which we write in Google can be translated into a Spark query in what we call DBpedia endpoint so that we can get the answer. So this was the issue. So one is in the search engine, the other is in social network analysis. Too much has been done on what we call on graph data. You might be aware about the extent to which progress has been done on what we call in gene disease association, which is an instance of graph data. So graph is now everywhere in the web. So my issue for this talk is how can I combine, you know, the knowledge graph issue was initiated from the semantic web research community. We are claiming like we can combine artificial intelligence, especially machine learning, and deep learning on what we call on this graph data. So one area is, for example, some of the data from DBpedia are incomplete. Some of the triples are incomplete. So we can use machine learning we can use machine learning to fill incomplete triples from knowledge graphs or from graph data. This is one issue. How? For example, 71% of the triples from DBpedia have no value for the country of birth attribute. They are for this attribute, there is missing data. So if we ask what the country of birth of a certain person, we cannot get answer. So using machine learning, I am claiming like we can discover. For example, the relation country of birth can be inferred from the relation city of birth. Am I clear? Through reasoning, we can infer. The other is some triples are, there are even some errors. Usually, if you see DBpedia, it is extracted automatically. We cannot expect this data to be perfect because it is extracted automatically. Even, in fact, DBpedia is extracted from semi-automatic data, what we call from Wikipedia. Some knowledge graphs are extracted purely from unstructured data. So we cannot expect it will be perfect. So there are some errors. There are some inconsistencies. Am I clear? So we can use machine learning to detect those inconsistencies and maybe the other, for example, inconsistencies like course X teaches person Y. Am I clear? Course X teaches person Y. Like by reasoning, we can detect that course cannot teach person. So by combining machine learning, we can detect errors. And the other is we can also use machine learning for data mapping, data set linking. The big graph, the big global graph is resulted from mapping. Some of them are done automatically. So like to extract answers for an entity from different sources, we have to link data sources to each other. So for this purpose, we can use machine learning. But the problem is, can we use the traditional machine learning? Sorry for saying traditional. It is to mean the machine learning approach that we are already familiar with. So the assumption is we cannot use conventional machine learning techniques for graph data. The reason is, the first one is, this conventional machine learning approach, they expect a data to be represented in the form of table, and like an object by attribute kind of table. But the graph data is not initially represented in this form. So one is either we have to have a mechanism to convert the graph into table, and that conversion can be either manually or maybe this manual conversion is time consuming, and one is we may lose important information. The other problem of this conventional machine learning approaches is models are built only from instance features. For example, if I want to predict the class of instance 1 from this data, the class of instance 1, the only information that we use is its attribute values. Am I clear? Like to predict the class of instance 1, we can only see the value of attribute 1, attribute 2, attribute 3. So from this value, we can predict its class. So the assumption is in what we call in conventional machine learning, there is independent assumption. One instance is independent to the other, but in reality, this assumption is wrong. Especially in graph data, this assumption is wrong. For example, if I want to predict the political affiliation of a social network user, I can use some additional information like I can predict what we call the political affiliation of a social network user from whether he or she opposes tax raise. This information which is attached to that social network user. We can also use, based on the number of friends he has that oppose tax rate. It means instances are not independent. The information that I get from instance 1 can also be used to predict the class membership of instance 2, which is not used in what we call in conventional machine learning approach. So we are claiming that we need some kind of technique. Well, I don't know what the name is. For this time, I call it deep learning because this is a common name given for this kind of techniques. So because a typical feature of deep learning is it automatically extracts features and it combines some multilinear processing, because the technique includes that one. We call it as deep learning. So usually for relational data and graph data, an equivalent approach for deep learning is a technique called relational learning. So relational learning, specifically a common algorithm from relational learning is inductive logic programming. Inductive logic programming. So what inductive logic programming do is, for example, if I want to predict Kabbade's nationality, and if I know that Kabbade is born in Addis Ababa, and Addis Ababa is located in Ethiopia, then inductive logic programming assumes Kabbade has nationality Ethiopia. This is like what you call this. There is deterministic inference. If this happens, this will happen. Kind of deterministic inference. The problem of this inductive logic programming is, one is, in fact, we all know that it is highly expressive. It is highly expressive because it uses first order logic for knowledge representation. But the problem is, it is difficult to scale this kind of techniques for web scale problems. Because in the web we have like 100 billion triples. If we want to make some learning on 100 million triples, we cannot make, it cannot be, inductive logic programming cannot be what we call scalable. And the other is, I and maybe the proponent of this approach, we believe that nature is not deterministic. We cannot say that if this happens, this always happens. If this happens, this will happen with a certain probability. So we need a mechanism that combines what we call the deterministic inference capability of inductive logic programming and probabilistic approach. So we come up with an approach which we call it as tensor factorization or tensor calculus. So tensor factorization or tensor calculus can be a new deep learning approach for graph data. This tensor factorization can be scalable for large scale relational learning tasks. There is highly parallel computation. The other is it balance expressiveness and complexity. It is good in what we call noisy and what we call heterogeneous data, which is a typical feature of the web. So we come up with tensor factorization. So before we apply tensor factorization, the graph data can be represented in a graph G, where G is a collection of vertex and what we call labels. So vertex are entities that appear in the subject or object position can be considered as vertex, and they have also relationship. So we can represent it in a graph. So if you see the RDF triple, particularly, it is based on subject, predicate, object format. So it is three-dimensional data by its nature. So we represent that graph into a three-dimensional data structure, which is called tensor. So given an entity I which appear in the subject position and entity J in the object position and a predicate K, this can be represented in a tensor like the entry can be 1 if there is a relationship between I and J, if there is K relationship between I and J, and it will be 0 if the K's predicate does not exist between the two entities. For example, Wikipedia, this is the subject, Ethiopia. The relation is capital, then the object is Addis Ababa. So there is a relationship between Ethiopia and Addis Ababa by the relation capital. So the entry will be 1. But Nairobi and Ethiopia has no relationship in terms of what we call capital. So it will be 0. So the tensor entry will be 1 and 0. Tensor entry will be 1 and 0. But the problem is, you know, we have 100 billion triples. 100 billion triples. You can imagine how the amount of or the dimension of data to be produced. So this technique needs dimensionality reduction mechanism. Dimensionality reduction mechanism. Usually, as I told you, it is 3-dimensional data. The dimensionality reduction mechanism like PCA and a CVD cannot work because they are designed for 2-dimensional data. So we use dimensionality reduction mechanisms for 3-dimensional data, which is what we call the DCOM, RayScan. These are dimensionality reduction mechanism. I don't want to go to the detail. For this research, we use the DCOM, but not in this original form. The first is to avoid what we call, to reduce the dimension, we come up with a sparsity promoting data structure. Sparsity promoting data structure, because many of the elements, many of the tensor elements are 0, then to reduce the dimension, sparsity promoting data structures are important, first of all. So in the DEDICO model, we introduce the sparsity promoting data structure, and the other is the algorithm for what we call to reduce dimension using DEDICOM is called alternative least square. So when the alternative least square performs, we introduce a weighting scheme, maybe which will be. So the performance of this paradigm is tested by factorizing Wikipedia and Yago, which are what we call the large scale knowledge bases in the web. For testing purpose, we use what we call Python data structures like CPy and maybe a collection of CPy. Then performance was encouraging. I think we are now comparing this approach with what we call recurrent neural network, and maybe so that we can conclude that this approach will be better for graph data than like the traditional deep learning approaches like recurrent neural network. I am an open data activist, so that I believe in openness, and also I am a librarian. So I put my code in GitHub. You can see the implementation by searching by Melkamu code contribution. Thank you.
Thank you very much.
Let me give this side with opportunity. Okay.
Yeah, thank you. Are there any local language resources, maybe in these structured types of databases? Is it possible to
Sorry?
Are there resources in local languages which you can use rather than using English?
Yeah. The Wikipedia is extracted from Wikipedia. We have Amharic Wikipedia. So that means we have Amharic Wikipedia. So in Amharic or in different local languages, we have now structured data. We started some work to to convert the Amharic Wikipedia to DBpedia. So we can assume, like, if we have CSV file, if we have Excel file, we have now graph data, because it is easy to convert from Excel or from CSV to graph data. Okay.
Any other questions? Okay.
Thank you, Doctor, for your presentation. I have two questions. One is, I was looking for some machine learning issues in the, maybe didn't get the detail, but is that something vectorizing the graph structure or applying machine learning on the process of learning the graph data representation? And the other question is, do you believe that the learning semantic of the meaning of the given unstructured text is not achievable without using a semantic structure or the graph learning?
Okay. I think this graph data, I have to remind you once again, from data science initiatives, there is something which is overlooked. That is data production. Am I clear? Because especially in developing countries, bottleneck is in data production. We have no data. So this graph model is already there. It is proposed by what we call the owner of the web. So we cannot be successful without considering the owner of the web. So there are already out there. Graph data is already out there, because the standard data publishing is RDF, which is a graph data. So my claim is, as a researcher, we can improve this graph data, which is purely from the semantic point of view, by combining with machine learning. So it is better to say learning than machine learning or deep learning confusion. So the issue is, we can have a learning, an artificial intelligence mechanism, and that mechanism in this research is taken as what we call deep learning, and the specific technique is tensor factorization, so that there are strong group that are working to introduce tensor calculus as one of the deep learning approach, especially on graph and relational data.
Yeah, looks like I sat right in front for all the questions. Thank you very much for your presentation. I have keen interest in graphs. I was looking forward to see what kind of evaluation you had over using your new method of conversion of graphs into tensors. That would have been really interesting. Could you speak to that? Then secondly, just to give clear advantages of using graphs, especially for the benefit of the audience, give clear advantages why you approve the graphs. In which sense would they be better than normal table data? Thank you very much.
Okay. So the advantage is, we advocate to get structured data. Having a graph data is a plus for me, because if you give me structured data in whatever format, I will have a graph data, because there are tools that convert data, what you call structured data, from the advantage of graph is it is visually appealing, to see for people. It is visually attractive. You know, people can search information by moving from node to node. Like by interacting with the data. If you see, for example, this one, it is about, this gives me information about Ethiopia. Ethiopia's capital, Ethiopia's what we call leader, Ethiopia's location, some information like this. So when I see this one, it is more attractive for me. And the other is even in gene disease association, which is an interesting issue. In gene sequence association, there is one gene, there is disease. So it is a graph. We can represent it in a graph. So that if we have some learning mechanism on this data, it will be. What was the other? It was interesting, but
your evaluation.
As I told you, the evaluation mechanism. The evaluation mechanism must be at web scale. It must be in a real time. So there must be some study on evaluation metrics. Because I said that the traditional metrics like recall and what you call precision, we can calculate precision, but we cannot calculate recall in real time. Because, so the evaluation is done only for entity linking purpose. There are some applications of this graph learning. One particular application is entity linking. So we do the evaluation on entity linking, but this evaluation is not compared with some techniques like the neural-based deep learning techniques, which we are currently doing. But for entity linking purpose, whether it create a good link or not, we make evaluation on the two data, so the result was attractive.
I have one question related to this one. Semantically, the basic platform is ontology. In related construction, having that we have this how to extract those relationships, particularly and taxonomic relationship. So how we can use this data factorization, say, for this kind of ontology.
Okay. Usually, when I talk about knowledge graph or RDF, someone will ask me about ontology. This is common. So, you know, have you seen how ontologies are represented? For example, when I say term 1 is synonym with term 2, I am creating an RDF data, a graph data. So the way ontologies are represented, or the data model to represent ontologies, is RDF. But we don't notice that. Like when I say this one is a subclass of the other, I am asserting some statement. One is a subject, the other is a predicate, and the other is the object. So when we build ontology, a basic data model that we use is RDF. In fact, but ontology and knowledge graph are not the same. Ontology is the top layer. Like we can use this graph, we can make reasoning over this graph by using ontologies, the higher layer. The RDF is not what we call the right choice. Am I clear? You know, the semantic web has goals. When we reach to the lower layer, we can move to ontology. But currently, the standard is RDF. The standard is RDF. So, but you can use ontology while you are using RDF. So I also believe even in ontology development, we can use learning. So there is ontology learning, which are based on machine learning, ontology learning. So we can combine.